Hello, this is Swapnil Dongre from IPS DAV Indore. In this video, we will see the numericals in NAD, that is numerical analysis and design, and the way to solve them. Okay, the first numerical is that you can see on your screen. The numerical is the population of city in a census taken once in a 10-year is given below. Estimate the population in the years 1925, 1975, and 1984. The following estimation is given here in years and population is given 1000. The question asks us to find the population in the years, that is, it asks us to estimate the population in the year 1925, 1975, and 1984. So what we'll do, from where we'll start, first we'll create the table. That is the difference table that you see on your screen. Here it is given the year, here is the population, and here is the basically the functions, differentiable function. Here our n is, that is number of years or number of columns, 1 2 3 4 5 6 7. This number of columns is 7, so our function will converge in 6 times. Our function will converge in 6 times. So this is basically a shortcut. So in 921, here years are mentioned here, population is mentioned here, and our functions, differentiable functions, are also mentioned here. The value, this is calculated from the difference between the next value and the first value, that is 42 minus 35 is 7, 58 minus 42 is 16, 84 minus 58 is 26, and so on. Similarly, 16 minus 7 is 9, 26 minus 16 is 10, and 36 minus 26 is 10. So it will go on till it converges at the final step. So what we have to find, the population. We have to estimate the population in the year 1925. So how will do it? Using Newton-Gregory equation, that is f of x equal to f1 plus del f1 x minus x1 upon h plus del square f1 x minus x1 into x minus x2 divided by 2h square. This is a formula basically, that is Newton-Gregory equation, equal to f1 plus del f1 u, this is basically u, x minus x1 upon h is u, plus del square f1 u into u minus 1 by 2, x minus x1, where x minus x1 is equal to uh plus x. As x1, we know that in the year is 1921, and what we have we have to ask to estimate the population in the year 1925. So x1 is 1921, that is the above year, and above year which is mentioned in the table, and the x is our the year in which we have to estimate the population. Therefore u is equal to 0.4. The u is calculated from this formula. Therefore, on putting value of x equal to 1925 in the above equation, f of 1925 is equal to 35 plus 7 into 0.4 plus 9 into 0.4 into minus 0.6. So we get our function in 1925 as 36.6. 1975 is near the end of the table, and thus we use the backward difference formula for calculating the for estimating the population in 1975. Since 1975 is near at the end of the table, so instead of coming from the forward difference formula, we can apply the backward difference formula, because the estimation closer to 1975 is 1981. So we can apply backward difference formula. Backward difference formula states that f of x is equal to f7 plus this is basically a backward difference operator, del f of 7 x minus x7 upon h, and so on. F of x is equal to f of 7 plus del f7 plus del square f7 u plus 1, and so on. Similarly, what we have mentioned earlier in terms of u, as uh is equal to x minus x7, as we are processing through a backward difference formula, so uh is equal to x minus x7. Therefore u can be estimated from this. Therefore f of 1975 is equal to 220 plus 100 into minus 0.6 plus the values of the formula has been placed in this value of the variable has been placed in this formula, and we have calculated the population in the estimated year, that is f of 1975 is equal to 124.48. The year now we have to estimate the population in the year 1984. So the year 1984 is outside the table of the values, thus we cannot interpolate. If we assume a similar trend is followed outside also, then in case of 1985 we can make the assumption that we get, so we can calculate the u from our assumption, that is 1985 minus 1981 by 10 here. So our u is 0.4. Therefore the f of 1985 can be calculated as follows. equal to 220 plus 100 into 0.4. Similarly, the first equation that we used to place the to calculate 1925 1975, similar equation is used here. So we got the value of f of 1985 as 432.4x. So this is the way you can calculate the you can estimate the population in the following years that we have done in 1925, 1975 and 1985. The second question is solve the following set of equation using Gauss-Jordan method. The below they have given us the equations, the following three equations, and we have to solve this set of equation using Gauss-Jordan method. And one more question is here: is row interchange necessary for the above equations? So we proceed to the solution. No row interchange is not necessary, though it is convenient. Mm, First, we'll took all the coefficients and make a matrix. 4 2 2 1 4 1 minus 2 2 minus 2 2 2 0 15 and minus 5. Then basically what we have to do, we have to make the elements of these matrices as zero as possible. So there is a small formula. If you want to make the first term of the second row 0, then what you can do, r2 minus r1 into the term which you want to make 0 divided by the term from which you want to make 0. That is, r2 is equal to r2 minus r1 into 2 by 4. r3 is equal to r3 minus r1 into 2 by 4. So this will make this second row's first term, that is a21 and a31 0. See, you can look here. The next step is that r1 is equal to r1 minus r2 into 36 by 6. That is, we have to make this element 0. 36, oh sorry, 6. So we are done here. 36 divided by 6, and similarly r2 is done. R2 minus r1 into 6 by 2. 6 by 2. So these two terms are made 0 in the following operations. Therefore, by making more and more zeros, we can estimate the value of x1, x2 and x3. Similarly, there are three equations will be formed, that is x1 is equal to minus 1110 divided by 36, that is minus 55 by 18. x2 is from the second row, that is 80 divided by 12, that is 20 by 3, and x3 is minus 200 by 72, that is minus 25 by 9. So in this way we can calculate the values of the variables and by using Gauss-Jordan method. So I hope you understand the lecture. Thank you.